Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, me and my group will present our plant design project with a title of Biogas Production from Pig Manure. Our group members consist of me myself, AMIRUL SYAZWAN, Usuki, Muhammad FARHAN Ashraf, EIRDHINA, and ALAA ANWAR. For our presentation outline, we will cover on the introduction, literature review, process screening, manual mass balance, economic analysis, heat integration, process and instrumentation control, hazard, and conclusion.
The intensive depletion of fossil fuel resources due to their huge utilization of energy in Malaysia, with the sudden fluctuations in oil prices and environmental pollution, all of these concerns has led to increasing trends towards finding a renewable and cost-wise green energy alternatives such as biogas, which is a clean and environmentally advantageous energy source generated from anaerobic digestion process. So in this project, pig manure will be our main feedstock as it is widely available and easily collected. Since the pig population in Malaysia is around 1.5 to 2 million, as it can be seen in figure 1, and the manure generated is about 14,000 tons per day. Beside that, rice straw is used as co-substrate due to the low costs and abundance of raw material based on the statistics shown in figure 2. Moving on to problem statement, the elevated utilization of energy in Malaysia has led to high dependency on fossil fuels. In this regard, the intensive consumption of these resources has caused the increased concern about the depletion of these non-renewable resources of energy. Therefore, cost-effective renewable energy alternative is used to replace the fossil fuels. With the increasing of the pig population, a large amount of waste is generated, especially in terms of manure. This situation could lead to unhealthy environment and increasing number of flies. Thus, pig manure is used as the main feedstock in this project. However, pig manure has low carbon to nitrogen ratio, meaning it contains concentration of ammonia greater than necessary for the microbial growth, which may inhibit the anaerobic digestion process. Therefore, to improve the nutrient imbalance and overcome the substrate deficiency, rice straw was used as co-substrate because it contains high content of carbon, which subsequently improves the carbon-nitrogen ratio of the process. Next, the plant design objectives are as follows. First objective is to build a biogas and biofilterizer plant with main feedstock of pig manure and rice straw as co-substrate. Secondly, is to design an effective and cost-economic process for the conversion of pig manure to biogas and organic fertilizers. Third objective is to attain a high purity and high composition of biogas and biofertilizer products that meets the market requirement. The flow of this plant design scope of work has started with intensive literature reading on market demand of products, as well as the composition of feedstock and the site plant location, and also the pre-treatment for the co-substrate and intensive literature on the available technology to convert the feedstock into the valuable added products. And then SPM Plus simulation was used for mass and energy balance and process optimization, whereas heat integration has been done using HINT software, and the strategy of the plant is emphasized using PFD and PNID, hazard study, and economic analysis. Moving on to literature review, basically there are 4 stages in anaerobic digestion process. In the first stage, hydrolysis, large complex molecules will be biodegraded by anaerobic hydrolytic bacteria to smaller soluble molecules. Second step is acidogenesis, where compounds such as alcohol, volatile fatty acids, hydrogen sulfides, and ammonia are formed. During the third stage, acetogenesis, products formed in stage 2 are further digested by acetogens to form CO2, H2, and acetic acid, which are then used as supplies for methanogens in the fourth stage. Methanogens converts the H2, CO2, and acetate into CH4 and CO2. Operating and environmental factors are considered in this project as well. For the optimum conditions, of carbon-nitrogen ratio is 30 and the pH is about 6.8. For the temperature conditions, it is observed that thermophilic digestion can produce more methane as compared to mesophilic digestion. Besides, its biogas production cycle is shorter, which means shorter HRT. And the best ratio for pig manure to rice straw is 65 to 35 weight%. Biological pretreatment of rice straw can increase biogas production efficiently. Hence, it's more preferred compared to chemical and physical because it has low cost and also causes no environmental pollution. Based on literature review about market study, the two products proposed for these projects are biomethane and biofertilizers. Figure 4 illustrates the global biogas market growth over this decade in different regions. The market value in USD billion is rapidly increasing, especially in North America, Europe, and Asia. Figure 5 shows the electricity generation per year from biogas production in Malaysia, which implies it is in high demand. Based on figure 6 and 7, global manure-based organic fertilizer demand in the coming years shows a very magnificent rate of growth, especially in Europe and Asia. For the plant location, Kampar is the best choice for our plant site. It is located in Perak State. It has the highest availability of feedstock and near to the seaport. Thus, it is a strategic location for the plant. It is also the best in terms of other aspects such as the land price, and also it has sufficient labor availability.
Hi, my name is Wasuki. So I'm going to present on the conceptual process design of our plant, which involves process screening and also manual mass balance. So now let's start with process screening. Basically, the whole process of our plant starts with the mixing of pig manure and rice straw, followed by the anaerobic digestion, and at last will be the removal of impurities for the methane produced. So this slide is actually showing the correct sequence for our whole process, which involves anaerobic digestion and also the removal of impurities of the methane produced. So anaerobic digestion can be divided into four, which are hydrolysis, acidogenic, acetogenic, and also methanogenic reactions. So logically, this is the correct sequence for the whole anaerobic digestion because based on the research we have done, acidogenic is actually using the products produced by hydrolysis as the process reactants, and acetogenic reactions will be using the products produced from acidogenic and hydrolysis reactions as its reactants. So same as the methanogenic reaction, it will be using the products produced by acidogenic, and also hydrolysis reactions as its reactants to produce methane. So after the anaerobic digestion process, we will be continuing the process by removing the impurities contained in the methane produced. So at first, we will be removing the water, which is having the highest percentage among all the impurities, followed by the removal of other impurities, and at last, we will be removing the hydrogen sulfate. The main reason that we removing the hydrogen sulfate itself is because it is a very toxic gas that cannot be contained in the methane produced. So now I'm going to show you the flow sheet obtained from Aspen plant simulation. At first, pig manure and rice straw will be mixed by using a mixer. Then they will be sent to a CSTR reactor to undergo hydrolysis and also acidogenic reactions. Then they will be sent to a UASB reactor to undergo acetogenic and also methanogenic reactions. So for now, the methane is already produced. We are going to continue the process by removing all the impurities from the methane. At first, water will be removed out by using a chiller, and then the other impurities will be removed out by using a water scrubber, and at last, we will be using an adsorption column to remove out the hydrogen sulfate from the methane produced. So now let me show you the simulation data. So the column that highlighted with yellow color is actually the last product that produced from our plant. And then the rows that highlighted with orange color is actually the components that contain in the methane. So for the water is about 0.6%, nitrogen gas is about 0.05%, followed by carbon dioxide is about 0.08%, methane is about 98.5%, and then followed by the hydrogen gas is about 0.8%, and also last, hydrogen sulfate is about 0.01%. So that's all for process screening, and I'm going to continue with manual mass balance. Here showing the composition of pig manure, and here will be the composition of pre-treatmented dry straw. So here will be the total composition of our feed, which containing moisture, carbohydrate, protein, and also fats. So the total feed will be 300 kg per hour, which means 200 kg per hour of pig manure will be mixed with 100 kg per hour of pre-treatmented dry straw. So the mass balance of our whole process will be shown in this file, which containing hydrolysis, followed by acidogenic, acetogenic, and methanogenic reactions, and also the removal of impurities from the methane produced. So now let's start with hydrolysis reaction. In this reaction, carbohydrate, soluble protein, and trialine will decompose into smaller molecules that can be used as reactants in the following reactions. So now let me take carbohydrate as an example. Before the calculation starts, we will balance the chemical equation. So after that, we will calculating the total carbohydrate content in feed by calculating separately in pig manure and also rice straw. So for pig manure, it is about 200 kg per hour of flow rate, and the percentage of carbohydrate content in pig manure is about 44.06%. So the total mass of carbohydrate content in pig manure is about 88.12 kg. This same with rice straw. So to take the total carbohydrate content in feed is to add them up, and the carbohydrate of the feed will be 154.12 kg. So the calculation is continued by calculating the molecular weight for each reactant, which is carbohydrate and also water. So to calculate total molecular weight, we times the molecular weight and coefficient together. So since the limiting factor of these reactions is carbohydrate, so we are going to use its mass flow, which is 154.12 kg per hour. So the molar flow of carbohydrate can be obtained by dividing mass flow from total molecular weight. So to get the molar flow of water, we times the molar flow of carbohydrate with the coefficient of water. Then to get the mass flow of water, we times the molar flow of water with its molecular weight. So for the products, it's almost same with the reactants. At first, we calculate the molecular weight, writing down the coefficient, and then we calculate the total molecular weight for products. For the molar flow, we will times the molar flow of carbohydrate with its own coefficient. Then for the mass flow, we times the molecular weight with the molar flow of the product itself. So at last, we total up the mass flow of reactants, and then we total up the mass flow of all the products. They should be the same. So this means that the reaction is actually balanced, and then we can continue with the next step. So it is actually same with the soluble protein and also trialine reaction. So here shows the composition of hydrolysis reactions. The compositions that left from hydrolysis reaction will be used in the following reactions. So let's continue with acidogenic. So at first will be the amino acid degradation, which involves serine and also lysine. And then will be the acidogenic reaction, which involves glycerol. So for serine and lysine, the calculation is actually same with the hydrolysis reaction, because they are a type of protein which can be considered as insoluble proteins. So just for the acidogenic of glycerol, since the glycerol is actually obtained from the hydrolysis reaction, so we are going to take the value from hydrolysis process, which is about 1.02 kg per hour of glycerol, and we insert it in this reaction, and then all the calculation will be the same. And we will also comparing the mass flow of reactants and also products. So now let's continue with acetogenic reaction. The calculation is actually same with acidogenic reaction. Just take all the mass flow from the previous reaction, and it is also the same with methanogenic reaction. Just at last, I added a reaction by adding extra hydrogen, to react with carbon dioxide so that we can get more methane as our products. So now let's continue with the removal of impurities from the methane produced. So the methane produced from the feed is actually 36.93%. Then we will remove the water by using chiller, and then we will remove the other impurities by using water scrubber. And at last, we will remove the hydrogen sulfate, which is a very toxic gas, by using an adsorption column. So this is actually the last products of our methane. So it's actually contain 97.5% of methane, followed by 0.05% of ammonia, and then followed by 0.01% of hydrogen sulfate, 2.37% of water, and then 0.01% of hydrogen, and at last 0.0004% of nitrogen gas. So that's all for the manual mass balance. So this is the comparison of data obtained from ASPEN plus simulation and also manual mass balance. So each streamline is compared and the percentage of difference are also calculated. So the overall percentage of difference is about 0% to 11.3%. It is not a very big difference. So it can be concluded that the data obtained from ASPEN plus is almost the same as the manual mass balance. So that's all for my part, and I'm going to pass to my group mates. Thank you.
In every feasibility studies of a project, economic analysis is an important element to evaluate a project whether it can produce a profitable product or not. On the other hand, it is one of the alternatives in decision making by making feasible comparison to evaluate the outcome of a project. In evaluating the process optimization, the measure of economic potential is required. Economic potential will determine which design will be chosen based on the high value of EP. Of this process will be pig manure as the main feedstock with an organic co-substrate which is wheat, rice, straw at 2:1 ratio in producing biomethane organic fertilizer. A few assumptions are to be made to simplify the evaluation where the cost of pig manure is not. So for EB1, the annual revenue cost will be minus with total raw material cost, and we will get 39,894,633 ringgit and 60 cents. So for EP2, which is EP1 minus with the annual total cost of utility, and we'll get 7,460,601 ringgit and 38 cents. So since both EP1 and EP2 gives a positive value, so we can proceed with the selected product and raw material that we choose. Next, so here are the source of utility for electric and water. So for electric, we get the source from Tenaga Nasional Berhad electricity tariff for industry, which is 37 ringgit per kilowatt. And for water is from SAJ Randhill Sdn Berhad water tariff. That gives 3 ringgit per cubic meter of utilization. So according to NS Energy, Denmark has one of the largest biogas plants in the world with an annual production of 41 normal meter cube of biomethane. So this production is estimated to generate energy at an equal of 45.4 megawatt of energy that is operated in early 2018. While in Iran, the biogas plant is still under development, where there are only 137 biogas plants in operating. However, the population in Iran is quite high, and therefore the electricity usage in the country is demanding. While in Poland, there are 24 agricultural biogas plants that are still under operation. For Southeast Asia market, a small-scale biogas farm is currently advocated in Vietnam. Many of existing plants are only using simple process, as they only processing a small amount of feedstock. It is also estimated that the manure-based biogas farm is 1.6 0.09 meter cube per day only. In Sri Lanka, this spends almost 12,000 USD to import fertilizer, which is the largest amount as compared to the other imported goods. While in Indonesia, which is the fourth most populated country in the world, in line with the high energy user, which is estimated to triple the number in 2030. So roughly 199.3 billion kilowatt hour of electric energy is consumed in Indonesia annually. In fact, Java and Sumatra is the highest populated area in those countries that leads to the highest usage of energy. Okay, so for heat integration part, the pinch analysis method is used in designing heat exchanger network to maximize the energy recovery from the process, as well as minimizing the amount of utility needed for the process. So by extracting the data from the process flow diagram, we can get one hot stream and three cold streams. Okay, next, so first we need to construct the problem table algorithm so we can proceed with the cascading. Okay, so by adjusting the cascade, we can get the pinch temperature. So here we got 298.28 Kelvin, and from here also we can get the QH mean and QC mean. So the minimum energy target for hot utility is 2166.22 kilowatt, while the minimum target for the cold utility is 185.55 kilowatt. So here is a composite curve that can be plotted by using the data tabulated in PTA. So by computing the data into HIN software, you can get heat exchanger network design. So there are 3 hot utility and 1 cold utility, but there is no heat exchanger since we assume our whole process is running at ambient temperature.
Assalamualaikum and hi, I am Farhan. So for my part, I will explain on the PFD, PNID and also process instrumentation control. So this is our PFD. So we have included in the stream, in each stream, the flow rate, temperature and also the operating pressure. So at the right top of the diagram, there is a legend which consists of 4 different shapes, which is circle, rectangle, diamond and parallelogram. So for circle is the temperature, rectangle is for pressure, diamond is stream number and the last one is for flow rate. At the top here is the equipment list and their equipment number. So next one is PNID. So here are the equipment summary for the major equipment, and here are their operating temperature and pressure. So I will talk more detail for process control in the next part. So next part is process instrumentation and control. So in this part we include 7 equipment, which is mixer, CSTR, USB reactor, chiller, water scrubber and also H2S remover. So in this part we focus on 5 elements, which is control adaptive, control variable, measure variable, manipulated variable and also type of controller. So for our plan, we actually use only one type of controller, which is feedback controller. So for the first equipment, which is mixer, the control objective is to control ratio of 2 feed stream, which is peak manual and also stream. So the measure variable for this equipment is ratio. So how we manipulate the ratio is we manipulate the flow rate of peak manual and also ratio. So for mixer, we install flow controller and flow transmitter for each stream. The next equipment is CSTR. For CSTR equipment, there are 3 control objectives, which is to maintain the temperature inside CSTR, to maintain flow of feed, and also to maintain level inside CSTR. So in order to maintain temperature inside CSTR, the measured variable is we measure the temperature inside CSTR. The manipulated variable is flow rate of feed stream. And the second one is we measure the flow of feed to CSTR from the mixer. So the manipulated variable for this objective is valve opening of feed stream. The last one is to maintain level inside CSTR. The control variable is CSTR level. What we measure is the level inside the CSTR itself. So the manipulated variable for this one is flow of product stream. The third equipment is UASB reactor. So there are 3 control objectives for this equipment, which is to maintain reaction temperature, to maintain flow of feed, and to maintain pressure inside UASB. So for the first one is to maintain reaction temperature. So we measure the temperature inside UASB. How we manipulate it is we manipulate the flow of inlet stream. The next one is to maintain flow of feed. The control variable is flow of feed. What we measure is the flow of feed to UASB, and the manipulated variable is valve opening of feed stream. And the last one is the pressure. So we measure the pressure inside UASB. The manipulated variable for this one is flow of product stream. So for UASB, we install 3 controllers, which is temperature controller, pressure controller, and also flow controller. So for next equipment is chiller. For chiller, there is only one control objective, which is to maintain pressure inside the column. The control variable for this one is the pressure inside the column. What we measure here is the pressure. So the manipulated variable for this one is we manipulate the flow rate of inlet stream. So in order to maintain the pressure, we install two controllers, which is flow controller and pressure controller for chiller. So the next equipment is water scrubber. For water scrubber, there are 3 control objectives, which is to maintain temperature of the column, to maintain column pressure, and also to maintain liquid level of the column. So for the first control variable is column temperature, which we measure temperature inside the column. The manipulated variable for this one is flow rate of feed to the column. For second one is to maintain column pressure. The measure variable is the pressure inside the column. So the manipulated variable here is outlet flow of the column. And the last one is to maintain liquid level of the column. So the control variable here is liquid level of the column. What we measure here is level inside the column. The manipulated variable is flow of production. And the second last equipment is S2S remover. There are also 3 control objectives. The first one is to maintain temperature of the column, to maintain column pressure, and the last one is to maintain liquid level of the column. The measure variable for the first one is temperature inside the column, which the manipulated variable is flow rate of feed to the column. The second one, the measure variable is pressure inside the column, the manipulated variable of outlet flow of the column. And the last one is to maintain liquid level of the column. The control variable is liquid level of the column. The measure variable is level inside the column. And the manipulated variable is flow of product stream. So for H2S removal, we install three types of controller, which is flow controller, level controller, and also pressure controller. And the last one is heat exchanger. For heat exchanger, there is only one control objective, which is to maintain the temperature of the outlet stream. So the control variable for heat exchanger is temperature of process outlet stream. What we measure for in heat exchanger is their temperature. The manipulated variable is the flow rate of process stream. So for heat exchanger, we only install one type of controller, which is temperature controller. So that's all for my part. Thank you.
Next is hazard and operability hazard. Hazard is defined as a technique used to determine all the possible hazards that may arise in the plant. So the jargon used in hazard notes parameter, deviation, cost, consequence, safeguard, and guide words. The example of guide words that might be used in hazard is less, more, and reverse, and the others. For node selection, the first node that we chose is on the mixer. So the parameter, first parameter is flow. For more flow, cost, parameter malfunction. Consequence, vary the composition of the feedstock. The action required install flow indicator and controller. Less flow, cause pipe leakage. Consequence, vary the composition of the feedstock. Action required to install flow indicator and controller. Deviation, no flow. Possible causes, pipe blockage. No missing happen for the consequence, and action required is to install flow indicator and controller. For high pressure, the possible cause is pipe blockage. Consequence, rupture on the mixer. Action required is to install relief valve. Low pressure, the cause is pipe leakage. Consequence, reverse flow. Action required to install pressure indicator. Next node is on the STR. So the parameter evaluated is flow. Backflow of mixture of feed, manure, and rice straw. The cause is by the valve malfunction or high bed pressure. Consequence, contamination and possibility for runaway reaction. Action required is to install check valve. Less flow, cause pipe leakage. Consequence, disturb the mixing process, and action required is to install flow indicator and controller. For no flow, the possible cause is pipe blockage. Consequence, runaway reaction. Action required is to install flow indicator and controller. Next is UASB. So for flow parameter, the deviation for more flow cause flow meter malfunction. Consequence, overflow on the digester. Action required is to do the maintenance work. Less flow, the cause is the pipe leakage. Consequence, not enough substrate for reaction, and action required to install flow indicator and controller. For no flow, failure of the pump is the cause. Consequence, no reaction occur inside the reactor. So for action required, maintenance work is need to be done. Pressure, for high pressure, cause is by the pipe blockage. Consequence, pressure build up in reactor and possibility of explosion to be occur. Action required is to install relief valve, high pressure alarm, and control valve. For low pressure, cause pipe leakage. The consequence is low flow biogas inside the reactor. Action required also to install relief valve and low pressure alarm and control valve. For temperature above 55 Celsius cause heating system inlet valve fail to close. Consequence, reduce the shelf life of bacteria inside reactor and pressure build up inside reactor. So the action required is to install temperature indicator controller and frequently check the temperature. For temperature below 55 degrees Celsius, cause heating system inlet valve is closed. Consequence, incomplete reaction, slow yield of biogas. Action required is to install temperature indicator controller and frequently check the temperature. Next node is chiller. So parameter the evaluated is flow and temperature. So for more flow, cause a flow meter malfunction. Consequence, the absorption of the water from biogas not efficient. Action required is to install flow indicator and controller. Less flow, possible cause, valve slightly open. Consequences, the absorption of the water from biogas not efficient. Action required is to check valve functionality. No flow, the cause is pump failure. Consequence, no absorption occurs inside the chiller. Action required is need to do the maintenance check on pump. For temperature above 15 degrees Celsius, high temperature for surrounding is the cause. Consequence, high efficiency of the chiller reduced. Action required, increased flow rate. Temperature below 15 degrees Celsius, possible cause by the temperature from the surrounding. Consequence, some water might not be absorbed by chiller, and action required is decrease flow rate. Next node is water scrubber. For more flow, cause flow meter malfunction. Consequence, absorption rate reduced, level increase. Action required, install flow indicator and controller. Less flow, the possible cause pipe leakage. Consequence, absorption rate reduced and level decrease. And action required to install flow indicator and controller. For no flow, the cause is by pipe blockage. Consequence, H2S will not be removed from the biogas, and action required is to install flow indicator and controller. For pressure, high pressure caused by the pipe blockage will lead to rupture on the column, and action required is need to install relief valve. For low pressure, cause pipe leakage. Consequence, reverse flow, and then action required to install pressure indicator. And last node is H2S removal adjustment column. So for all the parameter is same with the water scrubber and also the others jargons. So that's all for HAZOP.
In conclusion, upon the completion of this project, the targeted objectives outlines for PDP-1, which is to design a biogas production plant, is successfully achieved. An effective and cost-wise anaerobic co-digestion process of pig manure and rice straw has been designed to produce two value-added products, which are biomethane and organic fertilizers. The operating factors have been taken into consideration to optimize the plant and ease feasibility. Total annual revenues gained from biomethane was valued around 466,000, and the total profit obtained from organic fertilizer is about 39 million per year. The production of biomethane at its targeted industrial preferred purity of 98.5% is conceptually achieved.